Good morning, afternoon, or evening, everyone, wherever you are in the world. Welcome to our ChemDraw Connect webinar series. My name is Joanna Janas, and I'm Marketing Manager at Revity Signals. I will be your moderator for this session, and this ongoing ChemDraw Connect webinar series is an opportunity for you to learn about ChemDraw's features to effortlessly create eye-catching professional graphics that make your research shine. Today's topic is From Idea to Reality, Harness the Power of ChemDraw. A couple of housekeeping points before we jump in. This session is being recorded and will be available for streaming at revitysignals.com/chemdraw-connect. Please submit your questions through the questions box located on the right-hand side of your screen. As always, we want to hear from you. If you have any topic suggestions for our upcoming Connects, feel free to reach out to us on signals.events@revity.com. Now, I would like to introduce our speaker for today. Nicola Tribalau is the Senior Principal Marketing Lead for Chemistry here at Revity Signals. With 17 years of experience in drug discovery, he has not only provided direct project support and led teams, but has also played a significant role in establishing scientific standards and ontologies. Nicola holds a master's degree in chemical engineering with a specialization in organic chemistry, a PharmD, and a PhD in drug design from the University of Paris. Now I'll hand over to Nicola, who will talk you through the topic of today's webinar.
Perfect. Thank you, Joanna. I appreciate the intro. Good day, everybody. I'm really excited to connect with you today. Impatient to share with you some of the advanced features of ChemDraw. So the agenda for today is we're going to talk about integration of scientific resources. Before I do that, allow me to first have a quick reminder of ChemDraw and the fact that we have 3 different offerings. The reason I would like to do that with you is because it's in direct relation to the topic, because in some of the offerings, you will not access to all the features I'm going to describe. All right. So as we talk to integration of scientific resource with ChemDraw, you will see that we can do through ChemDraw directly in the interface instant reagent sourcing, finding vendors by browsing their catalogs. We can also find some safety information about the product that we might want to acquire. And thereafter, we will also look into literature reviews, how we can create new molecules and test relatively swiftly if there is a potential intellectual property on these compounds, and if there is novelty for you, if you want to patent your inventions, for instance. So let's jump into it. Just a reminder about ChemDraw, these 3 flavors, these 3 offerings, as we call them. ChemDraw Prime is typically the one most students have access to because it allows to really quickly draw molecules using your keyboard, using your mouse, and create publication-ready documents that you can, immediately, submit to journals, or you can also use, of course, to prepare your PhD documents. The second and more advanced solution is called ChemDraw Professional. There you have more advanced features such as color highlighting, 3D visualization, but also the Helm editor. That's for the biopolymers, peptides, artificial peptides, oligonucleotides. ChemDraw Professional can also do property predictions. That includes pKa, solubility, lipophilicity, but also proton and carbon NMR shift predictions. I'm going to show a couple of examples during the presentation. Finally, released last year in 2024, we have Signals ChemDraw. This is the most advanced version of ChemDraw, the one that has all the features from other tools, from both Prime and Professional, and that is actually built on the cloud. So you can actually use a browser to directly draw your molecules on the cloud and then share your documents and collaborate. So obviously that's the solution that most companies and integrated laboratories would choose, because this is another one that allows close collaboration, document sharing, sharing molecules, sharing your plans with different other laboratories or even companies. On the very last slide I have for you today, then we will mostly use ChemDraw, of course. I would like to introduce you quickly to the different scientific resources I'm going to talk about. So what you have here is four different scientific resources that we have integrated. There's actually a bit more in ChemDraw, but I will mainly talk about those four. The first one is called ChemACX. This one is curated by ourselves, by our scientists at Revity Signals. It's actually a collection of more than 700, close to 800 different supplier catalogs. So they include the main ones, of course, Sigma Aldrich, Fischer, Acros, but also smaller ones that have more like niche chemistry. They would also appear in our supplier catalogs. Interestingly, in that catalog, you will not only see that the structure is available from a supplier, but also that you can buy it at different amounts, at different levels of purity. This database called ChemACX is updated quarterly. Two other scientific resources well known, SciFinder and Reaxys, will also be discussed today. SciFinder is maintained by CAS, and it contains, like Reaxys, literature information. So molecules that have been described in journals, in patents, in books, in scientific reports would appear in such databases. So you see they contain, both of them, more than 100 million different substances and compounds. SciFinder will have information also about their physical chemical properties, their spectra, while Reaxys will also include some biological information. You see that their updates, the first one is updated on a daily basis, and Reaxys is updated on a monthly basis. So the examples I will be showing to you today will mainly use SciFinder because it's very similar to what you could see also in Reaxys. Finally, I will talk a bit about PubChem. It is maintained by the NCPI. It's a huge database that contains more than 100 million compounds coming from 700 and more contributors across the world. It is updated daily, and it contains information about the physical chemical properties of these molecules, but also biological data. For instance, when pharma companies perform high throughput screening, you know that they can screen hundreds of thousands up to 1 million compounds. And some companies have actually published their results there. It's a very interesting resource. The reason we're going to talk about PubChem today is because it also contains security information about molecules. So I will show you that indeed, ChemDraw is integrated to PubChem, and it's able to retrieve such information. You see two bars under these particular boxes, Cygnus ChemDraw and ChemDraw Professional. This is to indicate that Cygnus ChemDraw integrates all of these scientific resources, while ChemDraw Professional would only include SciFinder and Reaxys. One last information here. Cygnus ChemDraw actually has the ability for yourself or for your IT people to integrate any other scientific resource that actually has a so-called application programming interface. So if you look into our help documentation, you will have all information to do that. It's relatively straightforward. You just need to have API information from the scientific database that you would like to integrate within ChemDraw. So now let us switch to ChemDraw. So the molecule of today's it will be axitinib. It's a compound actually that is the active principle of a drug called Inlinta from Pfizer. It's been approved by the FDA to treat renal cell carcinoma. The main target, it has several targets actually, but the main target of this molecule, axitinib, is the receptor of a growth factor called VEGF. And its role is to actually inhibit the pathway of that particular receptor. So by the way, the drawing that you see here is actually drawn within ChemDraw. If you don't know that, within the templates, you have a number of bioarts to draw, for instance, cell membranes, to draw different receptors, different organelles like the mitochondria or cellular anaplastic reticulum, for instance. right? So the role of axitinib on that particular pathway of the VEGF receptor, which natural role is to enhance cellular proliferation and cellular survival, is actually to block this activity, because as you can imagine, in a cancer, you do not want to have cellular proliferation or cell survival. So to start with axitinib, what I would like to show you is first, like you probably know that there's a dictionary of compound that is included within ChemDraw. And if you have a license for ChemDraw Pro and Signals ChemDraw, you will see this particular button on the top that you can have. If you click on name to structure here, you can actually write the name axitinib, and it will pull out the structure from its dictionary. Okay. If you also need to convert the structure to a name, you also have a button to do that. Here it will convert, of course, into a UPAC name. So you have here on top. And if you find a UPAC name in a publication, it will ChemDraw will actually use an algorithm to decompose the name and rebuild the structure out of this. So if I click again on name to structure from that particular UPAC name, it will generate the structure of axitinib. As you can see, the orientation is different because that's not the one that's coming from a dictionary of structures, but the one that has been regenerated directly from that particular name. All right. So the next step of this presentation about axitinib is to talk a bit about its synthesis. So it's relatively straightforward. As you can see, it actually includes two main coupling steps, Magetta coupling and a head coupling, which is separated by some activation and protection steps. So what I wanted to show you at this step is that you can actually check if all those reagents are available. By the way, you can also check, of course, if your target molecule is available. So if I select it and I actually call my toolbar for integration features. So the toolbar is just showing it. So it's called the add-ins toolbar. So I'm going to put it here on top. And I'm calling here the functionality to retrieve information about availability of the compound. So that's in ChemACX. So you can call from that particular menu here, ChemACX Explorer. So let's see if it's available from different providers. So it's automatically load the molecule, as you see, as I call this particular tool, and I hit search. So here, very quickly, you can see that from the different vendor catalogs, you can indeed already acquire your target molecule. If you don't have the time to do the synthesis, you can acquire, like for instance, 10 gram for A to B for a certain amount at a certain purity. Okay, and you have here the catalog entry for that particular molecule. Right? If that price is too high for you, you can look for maybe another provider, maybe a different and better purity for you, because you might use that in some important biological tests. Okay, well, of course you can buy it already, but it might be also very interesting to buy the reagents to produce that molecule, not only to produce that particular one, but because maybe you would like to include some variations of these reagents and have some exploration around the structure of axitinib, like to do, for instance, SAR exploration, structure activity relationships, right? So let's see if you can easily identify this molecule also from the vendor catalog. So again, I'm going to do a search in my ChemACX Explorer. It loads automatically that particular molecule, and I do the search. So here again, you have information about the different vendors that propose that particular reagent. All right. If you have, instead of a structure, but you have, for instance, a certain name that you would like to look for, well, of course, you can browse the catalog using a name. For instance, suppose I want to search for xanthos, right? So I'm going to open the ChemACX Explorer. This time, it's not going to load to search for a certain structure. That was the previous one. So I'm going to remove the field here, and I'm going to search for xanthos. So just typing it here. So xanthos. So what it's going to do is to look for the entries that have xanthose as a synonym, right? So you see there is a number of entries about xanthose. Sometimes it's about a certain salt of it. But if I look into that particular entry, for instance, and these properties, you actually see that it has actually a number of synonyms associated to it, including xanthose. Okay. The sources, again, you have all the catalogs that can offer that particular reagent to perform the synthesis of axitinib. Okay, so that's what I wanted to share here at this level about the different reagent of your synthesis. Another important feature, of course, is that you can, for instance, predict, suppose you would like to check if you have the right NMR spectrum for that particular intermediate of the reaction. Here, if you have a ChemDraw Pro license or Signals ChemDraw license, you can check about the NMR spectrum of that particular entry. So you go to structure and you predict the proton NMR shift of that particular molecule. And you can see how the prediction is being made. So if you see with my mouse, I point on a certain peak of the spectrum and actually highlights in green also on the structure on top of it where that particular set of protons is. Okay, so this is the methyl group from actually the only aliphatic part of my molecule. Then you have all the aromatic protons that are here highlighted in turn. And then the most shifted proton is obviously the one from this pyrazole. Okay, so it's a good way for, of course, checking on the structure of the molecule and have an idea if maybe you have this obtained that particular intermediate, or maybe you have obtained a different one, and then you obviously can identify this through spectroscopy. Okay, let's close this one and go back to our synthesis. The third thing I wanted to show you is that for the different reagents, and also you could try to do it for the intermediates, but let's do it for this particular reagent. You can actually find what are the available safety alerts about this particular reagent. So this is where I will actually check on PubChem to see if there's any information about this particular vinylpyridine that I would like to use in my synthesis. So if I go back to my add-ins button, I can click here and you see it tells you it's about PubChem and it's going to retrieve the safety information of that particular one. Okay, so you see it's quite fast. It really identified well it was the 2-vinylpyridine, and it's you have to be cautious with it because it's not only flammable and corrosive, it also has toxicity, it's irritant, and it can have some environmental hazards. So you can easily copy all those hazard statements, copy the precaution statements code, and paste them, for instance, in your lab notebook. So that you are prepared to take all the precautions you need to manipulate this vinylpyridine. Okay, and you can do that, of course, for all the reagents. All right, now let's move on to another part of my presentation. What I wanted to show you is that we can actually design molecules, and ChemDraw is the right environment to do that. Let's start again with axitinib. And suppose you would like to work around this structure, maybe yourself develop your own inhibitor of the VEGFR and try to compete this molecule on the market. So there's many ways to do that. One quick way is, of course, to say, maybe this molecule, I can replace some of the functionalities by bioisoster. One classical bioisoster, for instance, I could propose is to replace the nitrogen of this pyridyl group here by a cyanide group. So let's make a copy of the axitinib as the reference and replace the nitrogen of the pyridyl group by a cyano group. Okay, so let's put a cyano here. Let's draw a triple bond, a nitrogen. Go back here and do a bit of a cleanup. Okay, now I would like to know if there's any intellectual property that prevents me from maybe, someday patent that particular molecule. So to do that, I can actually query either Reaxys or query SciFinder, because remember, they contain literature information, including what is described in different patents and journals. If there's a hit here, then this means it's already been described. So there is no novelty of that particular structure, meaning again, it's going to be difficult probably for you to patent that particular molecule. So let's check on SciFinder. Okay, so I just hit once the button on the top, and I select the type of search I would like to perform for that particular substance on SciFinder. So what I would like to do is to do a search on that particular substance, not as a reaction or as a reference or to look for supplies. What I would like to do is to find substances that are being described for that particular structure. So I hit the search button and automatically it will go to my browser, which I use to log on to CS SciFinder and search for that particular entry. So let's wait for a couple of seconds to load. All right. So what you can see is that you seem to have found quite a number of molecules, but none of them is the one that you have drawn. The one that you've drawn, you see, has generated 0 hits. So meaning it's actually already a nice idea, maybe to pursue. Another thing that you can perform to help you supporting, in the design of novel molecules is to look at the structure at the PDB. The PDB, is the de facto repository for a crystal structure of macromolecules, including proteins. And since axitinib is an existing drug, there is very likely that it is actually already crystallized with its target. So let's go to the website of the PDB. Sorry. Okay, and at the PDB, you can actually search directly axitinib here on the toolbar, and you see that you have a number of hits that are showing up, like this one, for instance. Another way that you can do a search at the PDB website is to do by smile string. And you know that from ChemDraw, you can actually convert a certain structure, like for instance, that of axitinib into a smile string by selecting the molecule and by doing a copy as and a smile string. So smile string, it's a line notation of molecules, and it's very commonly used to look for information in database, including at the PDB. So let's go back to the PDB. And we have found, for instance, one entry for axitinib. Let's see if there is more, actually. So I'm looking for, again, the small molecule axitinib, so as a chemical name here. And you see that there's actually many entries for axitinib, which has been co-crystallized with a number of protein, including its actual target here, in the case of the disease we were describing before. So let's have a quick look into that particular entry. So you have 3D information about axitinib co-crystallized here. One thing I wanted to show you, and it's actually a recent feature that we've been added. If you scroll down on this page, you will see that there is information about the small molecule axitinib from that page here. And you can actually download the 3D coordinates of axitinib either as a CDD file, or as an SDF file. So let's do that. And when you actually open that particular SDF in ChemDraw, let's do this. It's actually the bioactive conformation of axitinib that you actually retrieve. So look for all files, and here is the SDF. So if I zoom a bit so that you can see better, what you can see here now is actually a 3D conformation, but not a random one, the actual bioactive conformation of axitinib in VHFR, right? The one that is being described in that particular co-structure. So let's take it with us. I'm going to copy it, Control C, and paste it next here to my 2D structure of axitinib and the one with the cyano group. Okay, I'm going to orient it more or less in the same orientation. And I'm going to go back to the web page at the PDB to look for extra information about axitinib. If you scroll a bit up, below the 3D structure here, you see that you can have an idea of the ligand interaction that is axitinib with its protein. So that's going to provide us with valuable insight about the key interaction that axitinib has with target. So in the center of the screen, I'm going to zoom a little bit, you can see axitinib in its ball and stick mode here. I'm highlighting it here. And you can see the different interactions that it can present with the target. Okay, just reloading the page to show you in dash all the different interactions that axitinib has with VEGFR. I'm going to simplify it a little bit. So to remove the cartoon depiction of the polymer, I'm going to remove some water molecules. And now we can really see way better how axitinib, you recognize the pyridyl that I had replaced with the cyano group before, and the rest of the structure of the molecule. Okay, I'm going to put it more or less in that particular orientation. And to have it next to me as I design my molecule in ChemDraw, I will do a quick screenshot of that particular structure. Okay, excuse me a second. Oh, stop. Zoom out. All right. Okay, and I can paste this next to my molecules. I'm gonna make it a bit smaller. So it's going to be very helpful because I have now a good idea of what are the key interactions. So what are the atoms that I cannot change because they have a key interaction. So for instance, this particular amide bond that you see towards the end has actually a couple of H bonds. So it's going to be more difficult to replace than, for instance, an atom that does not have any H bond. Okay, so let's have another thing here. One thing we could do is to see how to replace this double bond by maybe an aromatic feature. So what we could do is to take again the structure of axitinib. And first thing I'm going to do is to try to manipulate it so that in the 2D structure is more or less the same as the 3D conformation, because that really is going to help me with the design of the molecule. So I make a copy of axitinib. And as you can see, even if I orient my 2D structure of axitinib in the same orientation as the 3D structure, there is a couple of things that are actually quite different. First off, so the top part, the amide has a different conformation, right? So what I can do to change the conformation, just select the subpart of it, and I go to object, and then I flip selection here. So this is going to flip, and you see it's now more or less in the same orientation as the 3D structure. I'm going to do the rest with the bottom part of the molecule. Again, here I need to replace the benzopyrazole part. So to flip it, sorry. So I'm going to go to object, flip selection. And finally, I'm going to do a last flip probably, or maybe two actually, to flip the bottom part. Hopefully I'm going to select enough. Here, object, flip. Yes, and then the pyridyl is in the right conformation. Okay, so now it's more or less the same as in 3D, as in this picture here I have. So I'm going to suggest to replace this double bond by maybe an aromatic ring here. It's also rigid, of course. It has very similar angles. So it's going to produce some sort of a naftil if you want. Okay, so I'm going to draw this. And let's aromatize. Okay, so that molecule would probably fit because you can see that you have enough room in the pocket of the receptor. Is it novel? Again, the same question. So let's check again with SciFinder. I'm going to load it. Search as a substance. Maybe I will search to show if it's described in some Marcus substructures. So allow it a few seconds to search. Again, no result. So might be again another good direction to look to look for such a molecule. All right. So you see, ChemDraw is not only a drawing tool, a communication tool, but it also is a research tool for you. You can actually capture all your ideas and maybe decide to prioritize them for synthesis. Again, I've presented you that you can search for the different reagents for your synthesis. You can look for structural alerts on these particular reagents, and then decide on a certain route of synthesis. I think I have addressed all the points I wanted to make with you today. I think you can actually put all your questions, if it's not the case yet, in the chat. So I would be really happy to start answering them at this moment. Okay,
That's great.
Yeah.
Thank you, Nico, for covering the material today.
Yes.
There are a few questions that we can have a look at, but yes, just a quick reminder to everyone, feel free to type in your questions in the questions box. We will be going through that. Nico, let me know when you're ready to tackle the questions.
Yes, we can start. Okay, so the first person, Sylvia, asked me if I can share documentation about ChemACX. I will certainly do. Um, um, Probably we have, I'm not sure about this, I'm checking with you, Joanna, or we have emails of people who have, yeah, of course. So I'm going to send this to you, Sylvia, after the meeting. If other people are interested, of course, I can also send this kind of information. Then this following question, who pioneered and worked the most on Signal ChemDraw? So Signal ChemDraw, is the latest offering we have. So it's a project that starts some years ago, and it's mostly developed by Reaxys Signals. Okay, so it's a very recent product. It's all cloud-based. It's a so-called SaaS environment. SaaS actually means software as a service. So that's more technical aspects of it. It actually means that if you have Signals ChemDraw, you actually don't need to install the software yourself. Reaxys Signals will take care of this for you, and you will also have all the latest features with automatic deployment. So it's very practical. And also for your IT people, your administrators, they can actually very easily control their licenses, how they've been used. So that's all the beauty of a SaaS environment, actually, that you have with Signals ChemDraw. I'm not sure I understand the following question. Is there a president of local government where somewhere in the world that not sure could pay for Signals ChemDraw? That I don't know. I don't know to which Geoffrey institution you belong to, but we have special offerings for actually academia and government institutions. And actually, you also have access to some other Signals products if you are an academic. Okay, so don't be aware about, don't be worried about the cost of it. It depends if you're a government organization, if you're in the academic institution, or if you are a private company. Again, a person asked about how is this available in Signals. So in Signals, you have actually when you use ChemDraw through a Signals ChemDraw license, you will have access to extra features. So this will be enabled for you, and you can have these buttons that I was showing by going again in the drop-down menus, and then activate the toolbar for the add-ons. Okay, I'm going to other questions. So is ChemDraw a free software? No, it's not a free software. We have special prices, again, depending on the profile that you are. If you're a student or if you're a professional in the industry, you are not going to pay the same cost for the license. Um, a person from University of Canada asked if the product's been shared with them already. Normally, if you actually try to get a license as a student for University of Canada or a person working for University of Canada, we actually, for Cygnus ChemDraw, have a list of all the institutions that have acquired a license. So you can, as if you want to purchase it, you can actually verify if you may already have at University of Canada such a license. And if that's the case, of course, you don't need to pay. You will directly have one of those licenses. Okay, I'm trying to find another question. There's a lot of duplicated questions, of course. So a person asks, how do I get the advantage if I'm a student? Well, it depends on the version you want to have. If you're a student and you want to have this advantage, they will not be available with the entry level ChemDraw Prime offering. You have to go with a ChemDraw Professional or to upgrade to Cygnus ChemDraw, as I was mentioning during the presentation at the beginning of this ChemDraw Connect meeting. So a person asks how to add the search engine onto a taskbar again. Yes. So let me share my screen with you. So going again ChemDraw. So you go to actually view. This is where you have all these different toolbars to this all these different menus, and it's called the add-ins toolbar. This one, add-ins toolbar. And so that's this particular toolbar. I'm going to show it again, add-ins toolbar. So that this one that you have here. Okay. With all these different add-ins. By the way, I've not shown this to you, but you can also search for patents that contain a certain structure in Google Patents. So it's another one that you can actually use. Let's search for patterns that contain this structure according to Google's databases. As you can see, it's actually converted into a smile string. Again, that's the typical way of representing molecules in databases. And let's sort by, for instance, the oldest patent that describes it. And so you can see that, for instance, axitinib, you have the structure here again, was probably first described in 1999 in this particular patent. And you can actually download the PDF of that patent where the structure of axitinib has been described one of the first times in a US patent here. Person asked for the price range for ChemDraw for university. I would recommend that you go on our website to do that because it actually changes every year, and you can actually request a quote and get a quick idea of the price range here. Yes, a person asked about Cynthia, the retrosynthetic software option. We have to inform you that at the moment we're decommissioning Cynthia from ChemDraw, so it's not going to be available anymore in future versions. Okay, I think I've browsed very quickly through all the questions. I think I've answered most of them already. There's again quite a bit of duplicates. A person asked about pKa values and dipole moment, etc. They differ in similar tools. Any particular reason? Yeah, the algorithms are a bit different. For instance, to calculate the dipole moment, you will need to have partial charges for the atom. So that really depends on the type of force field you have embedded in a particular tool. So ChemDraw has its own, of course, and therefore the values might differ between a tool or another one. All right, I don't see any more questions coming. I think we've answered most of them. Oh yes, I see a question about the accuracy of the NMR prediction estimations. You actually can have an idea. Again, if I'm going back to the spectra, okay, let's take axitinib as the example here, and generate a prediction on the proton. You can actually see an estimation of the quality of the predictions. So typically, you know, these models for predictions have been trained with other molecules, and they make estimation based on the similarity of the environment of a certain proton in these other molecules. If there's enough, statistically enough, I mean, results in the database that support a certain prediction for a certain environment of a certain proton, it will be shown in blue here, showing it is particularly good. Medium would be shown in magenta, and when it's a rough estimate, maybe because there is not enough statistics to back this up, it's going to be shown in red. By the way, you can see that it's the heteroatom NH, which are very often rough, because it really depends, you know, if there's, for instance, water contaminants, you will have a lot of shifts of these polarized hydrogens. So it means that in terms of statistics, in the model that is in the backend, there's the distribution around those protons are very large. While for instance, for an aliphatic hydrogen, it will be a very sharp distribution, and therefore there is a high confidence on the quality of this particular prediction. So you see actually most of the protons described here on the structure are being shown in blue, meaning there is a high confidence about the prediction here. Okay. Oh, by the way, here the prediction is being made for CDCl3 at 300 megahertz. You can change these settings if you go to the preferences and you go to ChemNMR, and you can switch the solvent between DMSO and CDCl3, and you can change the frequency of your NMR magnets depending on whatever you have locally to your lab. Right. Just checking if there is any more questions. So a person asks, can we draw a synthetic scheme for the molecule generated in ChemDraw? So I'm not sure I understand the question. If it's drawing like I've shown again for the synthesis of axitinib, scrolling up a little bit here. Yes, of course you can do that. You know probably that you have all the tools with the arrows. You can actually type all your reagents and very quickly generate such a diagram. There are databases about chemical synthesis. For instance, I think one is made by University of Arizona, if I'm not mistaken, and actually used it to generate this particular diagram for you today. The reason it cannot be integrated in ChemDraw is because these databases does not have an API. So ChemDraw cannot communicate with it. So the constraint, of course, is a technical constraint. ChemDraw has to have the possibility to communicate with this external database with which you want to have an integration. It's not the case of the database I've been using here to generate this particular diagram that you see on screen. If I actually find such a database with an API, I would be keen on showing to you at a later ChemDraw Connect meeting. Thank you very much for your attention. I was very happy to have you attending this ChemDraw Connect meeting today. Don't hesitate to register for the upcoming one, which will be in 2 months from now, approximately. Thanks very much for your attention.